Good morning, friends. In a series of lectures, I'll be discussing about the molecular spectroscopy. So, as a part of the series, today in the first session, I'll be discussing about the introduction to spectroscopy. And introduction, I'll be discussing about what is spectroscopy, what is its importance, and what are the different regions of electromagnetic spectrum, and also what are the different types of spectra. Then, followed by, I will be discussing about introduction to microwave spectroscopy. So, friends, we know that every day thousands of compounds are being prepared and published in the various journals. And whenever a new compound is synthesized in the laboratory, its composition and structure are to be determined. And in determining the structure of a compound, spectroscopy plays a very important role. So we have different types of spectroscopic techniques, and each of these spectroscopic techniques gives different information regarding the structure and the constitution of the molecule. So, what is this spectroscopy then? So, spectroscopy is the study of interaction of electromagnetic radiation with matter, giving rise to a spectrum with the help of which the structural and compositional information can be obtained. I repeat, so spectroscopy is the study of interaction of electromagnetic radiation with matter, giving rise to a spectrum with the help of which the structural and composition information can be obtained. So I said, spectroscopy deals with the study of interaction of electromagnetic radiation with matter. So when we say interaction between the electromagnetic radiation matter, the question arises, why should there be interaction? As all of us know, electromagnetic radiation possesses energy. All electromagnetic radiations are associated with energy. So also matter is associated with energy. Because matter is made up of atoms and molecules. And we have learned that wherever there is matter, there is energy. And wherever there is energy, there is matter. Without matter, there is no energy or vice versa. Right. So, since matter possesses energy, electromagnetic radiation is also associated with energy. So, whenever we place or irradiate a sample with electromagnetic radiation, there is a transfer of energy from electromagnetic radiation to the matter. Depending upon the nature of atoms and molecules present in the sample, the radiations of different energy are absorbed, and thereby, depending upon the energy absorbed by the matter, there will be different types of interactions between the electromagnetic radiation and the matter. Because of these differences in the interaction between different types of electromagnetic radiation and matter, we have different spectroscopic techniques. And electromagnetic radiation is not a monochromatic radiation, it is a polychromatic. In the sense, electromagnetic radiation consists of light or radiations of different wavelengths. And we all know that the energy associated with light or radiation is given by the equation E is equal to h nu, where E is the energy associated with the photon. We all know that light exhibits dual nature, so also matter exhibits dual nature. So when we consider wavelength of light, energy associated with the photon of that light is given by the expression E is equal to h nu, where h is Planck's constant, nu is frequency, and nu is equal to c over lambda. So we can also write E is equal to Sc over lambda, and 1 over lambda is equal to u bar x by lambda. So these are the three different relations with the help of which we can calculate the energy of the photon associated with the radiation of a particular wavelength. So when we look at these expressions, energy of the radiation is directly proportional to frequency. And when you look at this expression too, energy of the radiation varies inversely with the wavelength. So when we consider that energy associated with the radiation, energy of the radiation increases with the frequency of the radiation, and energy of the radiation decreases with increase in wavelength of the radiation. So as I said, electromagnetic radiation is polychromatic in nature. Depending upon the wavelength of the light associated with the radiation, the electromagnetic radiation are of different types. We can classify these electromagnetic radiations into radio waves, microwaves, infrared waves, UV visible rays or waves, X-rays or gamma rays. So when we look at the diagram, I have shown as we move up, there is increase in energy. And as I said, energy is inversely proportional to wavelength. When you look at this energy level diagram of polychromatic radiation, radio waves are at the lowest. In the sense, radio waves are least energetic waves, and gamma rays are highest energetic waves, and more than gamma rays, cosmic rays have got still high energy. And cosmic rays are not used in any spectroscopy techniques. I did not include that. So, looking at the energy of these waves, radio waves are having lowest energy and gamma rays have got the highest energy. And since energy is inversely proportional to wavelength, when you look at wavelength of these different radiations, radio waves are the longest waves having wavelength more than 1 millimeter, and microwaves has the wavelength ranging from 1 millimeter to 25 micrometers, and infrared waves have got wavelength ranging from 25 micrometers to 750 nanometers, and visible radiation have got 750 to 400 nanometers wavelength, and ultraviolet rays have a wavelength ranging between 400 to 1 nanometer, and X-rays have a wavelength between 1 nanometer and 1 picometer, and gamma rays have a wavelength less than 1 picometer. So when we look at these wavelength ranges, these are not the exact wavelengths. In roughly, look at different authors with slightly different ranges. So let's not worry about the exact range, and this is approximate range of wavelength of different radiations. So, since these waves have got different energies, these radiations, when they fall on the matter, they bring about different changes in the matter. There is a different interaction between different parts of electromagnetic radiation and the matter. So when a matter is exposed to radio waves, as I said, radio waves have got lowest energy. So the energy associated with radio waves is just sufficient to bring about the transition of electron or nucleus between nuclear spin energy levels and electron spin energy levels. In ESR spectroscopy, an electron transition takes place from one spin energy level to the other. In nuclear spin resonance, nucleus takes transition from one nuclear spin energy level to the other nuclear spin energy levels. So the energy gap between these spin energy levels is so low that radio waves have got sufficient energy to bring about the transition of electrons and nuclei between these spin energy levels, thereby giving rise to NMR and ESR spectroscopic techniques. NMR stands for Nuclear Magnetic Resonance Spectroscopy. ESR stands for Electron Spin Resonance Spectroscopy. Then when we consider slightly higher energetic waves like microwaves, microwaves have got energy sufficient to bring about the transition of a molecule between rotational energy levels. Hence, employing these microwaves, we have a technique called microwave spectroscopy or rotational spectroscopic technique. And when we consider still higher energetic waves like infrared radiations, so when the sample is exposed or irradiated with infrared radiation, the transition of the molecule between vibration energy levels is brought about, giving rise to vibrational spectrum or IR spectrum. Hence, this spectroscopy technique is called infrared spectroscopy. Then, UV visible radiations. Since energy associated with ultraviolet and visible radiations is more than that of infrared radiations, so UV visible radiations bring about electronic transition between electronic energy levels denoted by principal quantum number n. And that's why since electronic transitions are brought about by ultraviolet and visible radiations, this spectroscopic technique is called electronic spectroscopy or UV visual spectroscopic technique. And when we use X-rays, which are got still higher energy than ultraviolet radiations, whenever a sample is exposed to X-rays, X-rays have got energy to ionize the sample. So electrons are knocked out of the atoms and molecules, giving rise to X-ray spectroscopic technique. And using gamma rays, which are more energetic than X-rays, we have one more spectroscopic technique called mass bar spectroscopic technique. So, employing different radiations of electromagnetic spectrum, we have different types of spectroscopic techniques. And with the help of single spectroscopic technique, it's impossible to arrive at the correct structure of a molecule. Each spectroscopic technique gives different information regarding structure and constitution of the molecule. Therefore, when you have the data from different spectroscopic techniques about a molecule, then only it is possible to arrive at the structure of the molecule. So, what we learned is that depending upon the type of the radiation falling on the sample, different types of interactions occur between the electromagnetic radiation of the sample, and we have different types of changes taking place in the molecule or matter, giving rise to different spectra. So, once we know, have an idea of the different types of radiation and the different types of spectroscopic techniques. Now let us see what are the different types of spectra do we have. So we have the spectra classified into different ways. One of the ways of classification of the spectra is based on we have whether we are studying absorption, observed light or emitted light. So depending upon which radiation we are studying about, we have two types of spectra, namely absorption spectra and emission spectra. This is one way of classification. So what is this absorption spectrum? So whenever we allow the radiation to pass through a sample, it could be a solution or a liquid or a solid. So whenever a beam of radiation is allowed to fall on a sample, a fraction of the light is scattered, a fraction of the light is absorbed, and the remainder is transmitted. So there is a scattering of light. A fraction of the light may be scattered, a fraction of the light may be absorbed, and the remainder will be transmitted. So if we analyze this transmitted light, then the spectrum obtained is called absorption spectrum. In the sense, when we allow a polychromatic light to fall on the sample, a fraction of the light is absorbed and the remainder is transmitted. So, when we analyze this transmitted radiation with the help of a spectrometer, we get a spectrum. So, this spectrum consists of certain wavelengths which are absent. Which are absent in the sense these wavelengths of light have been absorbed by the sample. So, when we study the transmitted light, the spectrum obtained is called absorption spectrum. Right. So, we all know whenever certain amount of energy is absorbed by an atom or a molecule, so these atoms and molecules upon absorption go to the excited state. They move from a ground state to excited state, where the energy in the excited state is higher. And we all know all high energetic systems are unstable from the law of thermodynamics. From the laws of thermodynamics, any system in the universe tries to acquire as low energy as possible so that it will be more stable. Right? So, when a molecule absorbs energy from the radiation and goes to excited state, the excited state being unstable comes back to the ground state. So when coming back to the ground state, it will emit all the energy or radiation that is absorbed. So if we analyze that emitted radiation with the help of a spectrometer, the spectrum obtained is called emission spectrum. So we can broadly classify the spectra into two categories, namely absorption spectra and emission spectra. So examples of absorption spectra are infrared spectra, UV visible spectra, rotational spectra, etc. These are all the examples of absorption spectra. Then what are the examples of emission spectra? You might have studied in your high school level and PUC level, spectrum of hydrogen or atomic spectrum. In even physics, you might have studied spectrum of hydrogen and spectrum of sodium metal. Sodium element is alkali metal. So, hydrogen spectrum consisting of different series like Lyman series, Balmer series, Paschen series, Brackett series, Piffin series, Humphrey series. So, this hydrogen spectrum is an example of emission spectrum. So, when you look at the hydrogen spectrum, we have a group of series of bands. So, first group of series of lines is called Lyman series, which arises due to emission of energy where the hydrogen atom takes a transition from say n is equal to 2, 3, 4 or any higher level to n is equal to 1 state. So, whenever hydrogen atoms plunge from higher energy state to ground state as n is equal to 1 state, these transitions give rise to Lyman series. And when the hydrogen atoms drop from any higher excited state to n is equal to 2 state, that will give rise to Balmer series. Like that, when the hydrogen atoms drop from any higher excited state to n is equal to 3 state, it gives rise to Paschen series. So like that, when we analyze the spectrum of hydrogen, it consists of series of lines of different groups which are called Lyman, Balmer, Paschen, Brackett, Piffin, etc. So it's an example of emission spectrum. So also, if you are all of us are aware of sodium lamps being used as street lights, or mercury lamps, or neon lamps used as street lights. So if you analyze the light obtained from a sodium lamp, so the spectrum of light from the sodium lamp consists of two lines, namely called sodium alpha line and sodium beta line. So that doublet structure, two lines obtained or absorbed in the spectrum of light obtained from sodium light is also an example of emission spectrum. So also if you might have seen signboards which glow when light falls on this. So these are all signboards painted with fluorescent paint. So when light falls on this fluorescent paint, the molecules take a transition to higher excited state and immediately revert to ground state by giving out the energy in the form of radiation. So your fluorescent spectrum is an example of emission spectrum, or phosphorescence is also an example of emission spectrum. So depending upon whether we are analyzing the transmitted light or emitted light, we have absorption spectrum and emission spectrum. So this is one way of classification of spectrum based on the nature of radiation being analyzed. The other way of classification of the spectra is like atomic spectrum and molecular spectrum. So this is another way of classifying the spectrum. So if the matter being exposed to radiation is made up of only atoms like sodium metal, potassium metal, or lithium metal, or hydrogen atoms, or neon gas. Okay, so whenever the matter is made up of atoms, when such matter is exposed to radiation, the spectrum obtained from such atomic sample is called the atomic spectrum. Spectrum is singular and spectra is plural. And if the matter exposed to radiation or matter under study is a molecular sample, then the spectra given out by molecular sample is called molecular spectrum. And what is the difference in the spectral lines that we observe in the case of atomic spectra and molecular spectra? In the case of atomic spectra, like in hydrogen, spectrum are sodium spectrum are spectra of alkali metals, we have well-defined lines. So, atomic spectrum consists of well-defined lines, hence the atomic spectra are also called as line spectrum. On the contrary, molecular spectra consists of bands, hence these are called band spectra. So, atomic spectra are called line spectra and molecular spectra are called band spectra because in the case of molecules have got different types of movement like rotational motion, translational motion, vibrational motion and electron transitions. So all these movements together give rise to peaks or lines in the spectrum, make it complicated and converting lines into bands. Hence, molecular spectra in general are band spectra, whereas in the case of atoms, there is only one type of motion, is translation motion, but no rotational or vibrational motion. Hence, the atomic spectra give rise to sharp lines or distinct lines. Hence, atomic spectra are also called as line spectra. So, depending upon the type of particles that constitute matter under study, we have two types of spectra, namely atomic spectra and molecular spectra. So once we are clear about what is spectroscopy, what are the different radiations that we have in electromagnetic spectrum, and what type of interaction is possible between these different types of radiations and the matter, and having knowledge about the types of spectra, now let's move on to molecular spectroscopy. So just now we learned that molecular spectroscopy is the spectroscopy, the technique dealing with the study of interaction between the electromagnetic radiation and the matter made up of molecules. And I told you that examples of molecular spectroscopy are infrared spectroscopy, UV visual spectroscopy, X-ray spectroscopy, rotational spectroscopy, etc. The mass spectroscopy is an example. Of course, that's not absorption. Okay, it's something different from these spectroscopic techniques. So, under molecular spectroscopy, today we will be discussing about rotational spectroscopy, which is also called as microwave spectroscopy. So, microwave spectroscopy is an example of molecular spectroscopic technique. So, whenever we consider molecules, it could be a diatomic molecule or a polyatomic molecule. So, molecules are associated with different types of motion, namely rotational motion, vibrational motion, and electronic motion or electronic transitions. We do have transitional motion as a translational motion. And we know this translation motion does not contribute much towards the total energy of the molecules. So only these are the motions, different motions of the molecule which contribute to total energy of the molecule. So when we consider energy associated with a molecule, that's E total. So total energy of the molecule is equal to the sum of rotational energy, vibration energy, and electronic energy. And all these energies are quantized. You know the meaning of quantization. Means if energy is quantized in the sense there will not be continuous values of energy, only discrete values, only certain values of energy are possible. That's the meaning of quantization. Let's not go into details of what is meant by quantization. So all these energies are quantized. And when you look at the magnitude of these energies, namely rotational energy, vibration energy, and electronic energy, rotational energy is less than vibration, far less than vibration energy, and vibration energy is far less than electronic energy. So according to Born-Oppenheimer approximation, total energy of the molecule is the sum of rotational, vibrational and electronic energies. And when we look at the magnitude of these energies, rotation energy is less than vibration energy and it is, in turn vibration energy is less than electronic energy. And all these energies are quantized. So there are certain values of energy possible. So, if you consider electronic energy is denoted by principal quantum number 1 and 2, as I studied in atomic structure, electronic energy levels are denoted by principal quantum number n. So, in between two electronic energy levels, there are vibrational energy levels denoted by vibrational quantum number v. And between a pair of vibration energy levels, there are rotational energy levels. I said all these energies are quantized. Since energies are quantized, we have energy levels corresponding to each of these motions. So, with respect to rotational motion, we have rotational energy levels. With respect to vibration motion, we have vibration energy levels. With respect to electronic transitions, we have electronic energy levels. So, when you look at this energy level diagram, between a pair of electronic energy levels, we have vibration energy levels denoted by vibration quantum number V, and between a pair of vibration energy levels, there are rotational energy levels denoted by rotational quantum number G. Like that, between each pair of vibration levels, there are rotational energy levels, and in between each vibration electronic energy levels, we have vibration energy levels. Again, in between vibration energy levels, we have rotational energy levels. So, if a molecule is to be transferred from one rotational energy level to another, the energy required is lesser compared to the energy required to transfer a molecule from one vibration energy level to the other. So also, the energy required to transfer an electron from one main energy level to the other energy level, electronic energy level, energy is required is still more. Therefore, when you look at the energy required for these transitions, energy required for this transition, and energy required for this transition, it's quite clear that these transitions require lower energy than this transition, and this transition requires lower energy than this transition. And the transfer of the molecule between different energy levels can be brought about by using microwaves. Because energy is so less or just sufficient to transfer the molecules from one rotational level to the other. Hence, we call this as a rotational spectroscopy, which employs microwaves. And to transfer a molecule from one vibration energy level to the other, we require higher energy radiation, so we use infrared radiation. Therefore, we have infrared spectroscopic technique. So infrared radiations always bring about transitions between vibration and energy levels. And the energy required for transferring electron from one electronic energy level to the other electronic energy level is very high. So we use either ultraviolet radiation or visible radiation, and hence this is called as electronic spectroscopy. So let me stop here. In the next session, we should continue about rotational spectroscopy. Thank you.